topics. Oh, this meeting is being recorded. Thank you for letting me know, Zoom. I love it. I have the options to continue or leave meeting. No, I'm definitely not going to leave the meeting. I'm going to make sure I click the right button. There we go. Still here. So yeah, happy to be here. And some of the things I'm going to talk about, just a brief outline, are some common machine learning problems. So those are problems that computers can really help solve. And they're very broad categories, but these are classification, regression, and clustering. So the idea with a classification problem is when you have information about something and you're trying to decide what category it belongs in. So an example in maybe the medical field could be looking at someone's genome, like a DNA, and deciding whether they're at risk or not at risk for a particular disease, genetic disorder, or looking at an X-ray of someone's lung and trying to decide whether or not they have lung cancer. There's really, really cool stuff that machine learning algorithms can do that can do almost as good a job as expert doctors and way faster. And so that's pretty neat that they can analyze maybe like a tumor or something and decide whether it's cancerous or benign. Something like Gmail or anything that scans your messages for spam will look at an incoming message and try to determine whether it's a spam message or a legitimate message. And then it'll filter out the spam messages and let the real ones go through. So anything like that where you're assigning something to a category is a classification problem. So they come up all over the place. Financial transactions, whether something's fraudulent or not, or something like that, just a classification. On the other hand, regression is where you're taking something and some characteristics of an object and trying to assign a numerical value to it. So that would be something like maybe trying to predict the price of a house based on, how many rooms it has and like how many bathrooms and the square footage and whether it has a pool and all of these different factors. So you can have all of these different things that you know about something and use that to try to predict the price of a house. So that's not putting it into a category, but that's giving it a number, assigning a numerical value to it. So that's used a lot of the time in like finance related things, lots of times with that, if you're assigning a price or a cost to something based on its characteristics. And then a third type of machine learning problem is clustering. So this is kind of similar to classification. There's often a sort of a blurry line between those two types of problems. But the basic idea with clustering is trying to group similar things together in some way. So an example of this might be like a news aggregator. So if you just like go to Google News, it puts similar news stories together. Or something like, if you buy something or you listen to a particular song, it'll suggest other songs that you might be interested in based on how similar they are. So the clustering, there are many different algorithms, but a clustering algorithm would look at how similar things are to each other and try to put them into groups without necessarily the user telling them what the groups should be in the first place. Oh, cool. Ken says that you have someone who works out in medical classification. That's awesome. Ooh, that would be so cool. I'd love to hear more about that. That's a great opportunity for you. So clustering, again, another example could be looking at your customer behavior. And so maybe trying to market things differently to customers who use your product a lot versus people who use your product relatively infrequently. And you might send different types of ads or different types of social media engagement strategies for those different types of customers. And so clustering can sort of take their characteristics and group them in a way that you can hopefully get something useful of. So those are, again, just three very broad categories of machine learning problems. And I'm going to give an example of each one of those and how statistics plays a role in the problem. First one, I'm going to give a little bit of background first. And if you want more math, let me know. And if you want, if that's enough math, then also let me know. So I'm going to do a little bit of math and then tell me, I'll do a poll in the chat. I love your system. I'll do a poll after I do a tiny bit of math to see if you want more math or that's enough math. So imagine that we have a test for a disease, whatever, a relatively rare disease that affects 3% of the population. And this test has a 5% false positive rate and a 1% false negative rate. So that sounds like a pretty accurate test, only like 5% being wrong in the direction where you don't have it, but it says you do, and 1% the other way, where you do have it, but the test says that you don't. So with this test, imagine that you test positive for the disease. How worried should you be? How likely is it that you actually have the disease? And it's not immediately obvious how to combine these numbers here, the 3%, the 5%, and the 1%, but they'll all play a role in determining this probability. And the rule that we can use to figure this out is known as Bayes' rule. And so what I'm going to do is draw a little diagram here. Imagine here's this person, a very boring person, and either they have the disease or they don't. So if they have the disease, we know there's a 3% chance. And that means that 97% of the population does not have it. So if we think about the sort of the data flowing, only 3% of it is going up that top branch and 97% of the people are going down that bottom branch. And then if you have the disease, oh, sorry, let's go the other way. So if you don't have the disease, there's a 5% false positive rate. So out of all of these people, this 97% of the population, 5% of those will test positive, and the rest, 95% of those 97 will test negative. Similarly, for the 3% that do have the disease, we know that this is a pretty good test. It only has a 1% false negative rate. So negative rate here, that's going to be a false negative. That's only 1%. And the positive is 99%. So again, this 99% is sometimes called the detection rate. The false negative rate here is that 1%, false positive rate is 5%, and then the true negative rate is down here. So we can think about, if we start here, you're going to flow through one of those 4 paths. You're going to end up in one of these 4 places. And the way that it could end up with a positive test, there's actually 2 places, right? We could end up here or we could end up here. And in both cases, the only information we have is that the test was positive. So we could figure out the probability of ending in one of those 2 spots. Well, the top branch here is 3% of the population and then 99% of that. So that's going to be 0.03 times 0.99. Which is, gotta get a calculator, can't do that in my head. Probably someone can do it faster than me. 0.03 times 0.99, 0.0297. 297. And then these folks down here, 97% of them do not have the disease, and 5% of those will test positive anyway. So this is going to be the 0.97 times 0.05. And that is 0.97 times 0.05, 0.0485. So altogether, if we just add those two, plus 0.0297, 0.0782, so 7.82% of the population are going to test positive. But we can't tell just from that test which group they were in. We want to think about, out of that 7.82% of the population, how many of them actually have the disease? Could anyone think what we would want to do with these sort of numbers that we have so far to determine the probability that if you test positive, you actually do have the disease? What would your intuition tell you we should do next? It's a tricky question. So we know that 7.82% of the population has tested positive. Out of those people, what proportion of those people are the ones that actually do have the disease?
Again, if you don't feel comfortable doing it in the general chat, just because you don't want to get it wrong, you can message any one of us as well.
Sure. Yeah. Sorry, I should have made that clear. Also, there's no shame in being wrong. If you make a guess and it's wrong, that's okay. That means you tried. This isn't a test, I promise. Well, let's think about it this way. If I knew that like 20 people had like a car, or let's say I have 20 people are in a group, and a certain all of them flip a coin, let's say, and I pick 10 of them. No, this is a really bad example. Never mind. Forget it. I'll just sort of tell you what happens next. So we know that 7.82% of the population tested positive. But those positive tests are made up of these 2 groups, this just under 3% and this 4.8%. So if all we know is that we tested positive, which is the 0.0782, the probability that you have the disease is just the probability that you belong to this group rather than that group. So the probability is going to be the probability 0.0297, the probability that you have the disease and tested positive, divided by the probability that you tested positive, which is going to be equal to, oh, someone put it in the chat, yes. 0.0297 divided by 0.0782, which is 37.9%, basically 38%. Which seems really low, right? We had this test and it sounded super duper accurate, right? Only 3%, 5% false positive, 1% false negative. And this is telling us that if we get a positive test result, we're only 38% chance that we actually have the disease. Can anyone think why this number is so low compared to, it sounded like this was a pretty accurate test? I'll give you a clue. It has something to do with this number here. Because this disease is so rare, we end up with a large number of false positives. In fact, more false positives than true positives. Because even though just a really small percentage of the people who don't have the disease test positive, there's so many more people going down this path, right? Way more people are going down this path that we end up with more people here at this ending point than this ending point here. And that's why this 38% is much lower than it sounds like it should be based on the accuracy of the test. So that's kind of a weird little counterintuitive thing that even with this really accurate sounding test, we end up with this relatively low probability of having the disease given that you're testing positive for it. Yeah, exactly. It's skewed by the relative higher false positives. Oh, that's Ken. That's why you're so smart. I was like, oh, who is this genius? That's right. Yeah. So 1 in the chat if you want more math, 2 in the chat if that was enough math and you want to see a machine learning example. I won't be insulted either way. I have 1 vote for math. Let's go. Got a 2, no worries. A couple of 2s. Okay, we're tied. 1, 1, 2 2s and 2 1s.
I got a direct message for a 1 as well.
Okay, we got a 1, another 1. I'll do it really quick then. How about that? I'll do a quick math. So how this works basically in terms if we want to generalize this idea of Bayes' rule, we can think about letting like whether or not you have the disease be the event A and whether or not you test positive be the event B. And what we're looking for is the probability of having the disease, probability of A, given that we know that you tested positive. So this line here, this magical line means given or knowing that. So we're looking for the probability of A, that you have the disease, given that or knowing that you tested positive. And what we've done here in this calculation is we've basically said, well, first we need to have the disease and then test positive given that we have the disease. And we want to divide that in total by the probability that we test positive for the disease. And that's known as Bayes' rule. And what we're doing here, we can see we're sort of flipping the direction. We want the probability of A knowing that B has happened. And to find it, we use the probability of B knowing that A has happened. So we flipped the direction of the conditioning. And that's what Bayes' rule allows us to do. It allows us to take conditional information in one direction and flip it to the other side. So that's Bayes' rule. If you've taken data, you'll know this, but now that we have that under our belts, even if you haven't, I want to talk about a machine learning application, which is known as the naive Bayes classifier. So this is a classifier, and remember in machine learning, that's something that's goal is to put something into a category or assign something to a group. And there might be multiple types of evidence to consider, but the basic idea is the same thing. You're trying to use Bayes' rule. You're trying to find the probability that you're in category 1, let's say cat 1, given the evidence. And we're going to use Bayes' rule, which means we're going to find the probability of being in category 1 times the probability of the evidence given being in category 1, sorry for squishing that there, divided by the probability of the available evidence. So we're going to use Bayes' rule the exact same way that we did before and try and figure this out. But sometimes there isn't just one piece of evidence to consider, right? In the example we just did, there's only one piece of evidence, which is the result of this one test. In general, in machine learning problems, there might be lots of different pieces of evidence to consider. And I want you to think of some examples here. Imagine you were trying to figure out which profiles on some social media site were fake. So like there's a huge problem with fake Twitter bots or whatever, or like fake Instagram, fake TikTokers, whatever. So, or just trolls in general. So what would be some features that would tell you as a human, not just as a machine, but as a human, that maybe this isn't a real person? Does anyone have any suggestions? You can type them into the chat or just unmute and shout them out. Huge amount of followers, right? That, like, especially if it grew really quickly, because you can pay for followers. Yeah. So let's say, I'm going to say like quick growth in followers. Especially if lots of those followers look like they're fake as well. They could be paid. You can buy followers. Any other thoughts? What might mean someone is, some profile is fake? Okay, yeah. Very few likes and comments, right? There are lots of followers that aren't actually engaging with the content. If there's lots that are engaging, they're probably real. I like that. Lack of updates or stories in history. Yeah, that could be a good one. So few updates or few posts. Any other thoughts?
I got one direct message saying like they kind of like spam the comments with like click the link in my bio.
Oh yeah, just like links or like spamming the comments or whatever. Yeah, for sure. Spamming comments with links. So you can kind of look at the behavior of this account. You could even think about like if they don't have a profile picture. That's not a guarantee, but that could be something like they don't have a profile picture, or if their username is just like user 75315, whatever, like if they have a non-unique, so I'll just add that here. There's lots of, these are all really great. Yours are great too, but like no profile picture and like a generic username. So tons, again, there's lots more even than just these, but really great suggestions. Thanks, Paul. That could indicate that maybe, this isn't a legitimate account. So what the naive Bayes classifier does is it's a way to combine all of this evidence together. So it basically assumes that these features, so having a quick growth in followers, few posts, no profile picture, generic username, and spamming content or spamming links and comments, these 5 features are independent given that the profile is real. They all have a certain probability of happening independently of each other given that the profile is real. And they have a different probability of happening given that the profile is fake, or knowing that the profile is fake. And something that has a big difference in those probabilities is going to be really good evidence in one direction or another. So if real accounts are maybe 5 times more likely to have a profile picture than fake profiles, then that's a really useful piece of evidence. And the naive Bayes classifier lets you combine them all together using Bayes' rule. So essentially what you would do, I'm not going to go too heavy on the math, is this probability here, the probability of the evidence, you would split it into 2 cases, whether it's given that it's real or given that it's fake, and then take the probabilities of each of those features happening, multiply those each together, and then add them together. And same thing on the top, then you'd just be looking at the probability of being fake by taking the probabilities of each of these features given that they're fake and multiplying them together. So that's kind of a cool way to combine evidence really easily, and that's called the naive Bayes classifier. I want to move on. I got 7 minutes left. Okay, I can do this. To my second example, which is a regression example. So that's where we're trying to figure out a numerical value for something given some features. So question for you, some background. What do you think? How many times do you sneeze in a year? Any thoughts? Average number of sneezes per year? 500? Sure. Yeah, it's probably about that. I've heard it's like around 300 or something. Of course, it's going to be different for every person, different depending on whether you have allergies or not, different depending on where you live, all sorts of things. But it's a number of things that happen in a period of time relatively randomly. Or we could think about looking at traffic patterns. So how many people cross a particular bridge on each day, or how many financial transactions occur every minute. these kinds of questions are relatively nicely modeled by something called a Poisson distribution, which has nothing to do with fish. It's just the name of the mathematician who came up with it. But the basic idea with this distribution is it's counting up how many times something happens in a long period of time or a short period of time, any amount of time, where there's no theoretical maximum. Like you could have them occur as often as you like, and they can occur randomly at any time. They don't only occur like according to a strict schedule. And so with this Poisson distribution, what we can do is find the probability that exactly k events occur in 1 unit of time, and it's given by this expression here. So this is e to the negative lambda, lambda is a parameter, lambda to the power of k over k factorial. And if you haven't taken data, I want to explain what that means. I'm not just very excited about this formula. K factorial is k times k minus 1 times k minus 2 times k minus 3, all the way down to 3 times 2 times 1. So 1 factorial is 1, 2 factorial is 2, 3 factorial is 3 times 2 times 1, which is 6. 4 factorial is 4 times 3 times 2 times 1, which is 24, etc. It grows very quickly. So if we wanted to know what's the probability that there were exactly 10 people crossing a bridge in one particular day, we take e to the negative times the parameter, that parameter to the power of 10, and divide by 10 factorial. So this is kind of a way of measuring how many times something happens in a fixed amount of time. But the rate here, this parameter lambda here, might not be constant, right? People might sneeze more during allergy season than not during allergy season. People might cross the bridge more when it's a sunny day versus when it's raining. More financial transactions probably occur during business hours than not during business hours. More occur on weekdays than on weekends. And so there's all sorts of seasonal things that could influence this rate lambda, and they could be different at different times. So again, could be the weather, could be the time of day, the time of year, the time of week, whatever. All these different things could influence it. And we can call these characteristics regressors, or sometimes explanatory variables or predictors, and just call them x's. So x1i is the first factor that might affect the outcome for observation 1, x2i is the second one, etc. And then we're going to define a new value for our parameter that has a little subscript I here based on the unique characteristics of that ith observation. So if I is, say, a weekday at in the spring, then the factors that affect it are going to be according to that I. And we put them together into this formula here. So e to the power of this combination, beta 1 times xi1 plus beta 2 times x2i, etc., where these beta j's are known as parameters. So those are basically, or coefficients, those can be estimated using machine learning, especially like R and Python is really, really quick and good at doing this kind of thing, but there's lots of different methods for estimating the best possible values of those betas to get you the best possible estimate of our rate parameter here. And then once we have that, great, we take that lambda I and plug it into the same formula as before, and we'll have the best possible estimate of the probability for that unique day or that unique period of time that depends on these other characteristics. So it's not just assuming that the sneezes are constant throughout the year, or the people are constant, or the transactions are constant. We can have it depend on the characteristics of the day, or the minute, or the hour, or whatever. Alrighty. I think I have 3 minutes left to do my last example, which will be fine too. And this is a sort of a clustering method or a clustering problem, also kind of related to a classification problem. This is a fun one. So imagine we have a whole bunch of data on the heights and weights of some cats and some dogs. And we'll say cats are denoted by these O's and the dogs are the X's. So the weights, obviously dogs generally bigger and heavier than cats, not always though. There's a couple of really small dogs here, little tiny ones, and a couple of big cats here, but they're all sort of graphed here, the height and the weight. If we had a new animal and we didn't know what it was, let's say it was here, how do we know if it's a cat or a dog? Just by looking at the height and the weight. Obviously, like if we were a human looking at it, we can say that is clearly a dog or that is clearly a cat, but machines don't know what cats and dogs are. They can just take these pieces of information, the height and the weight, and try to make a decision. So there's a few different ways to do it. One way is to sort of build a decision tree. So to look at this data and say, it looks like all the cats are, less than this height. And so we're going to say, if an animal is above that height, it's definitely a dog. And if it's below that height, then we'll look at a second question and we'll say, all right, if it weighs less than, say 7 or 8 kilograms, then it's definitely a cat. So you have a decision tree where you basically say, first, how tall is it? If it's above this height, it's a dog. If not, we'll go to the second question. All right, now, are you above or below this weight? If you're below, you're a cat. If you're above, you're a dog. So it's a 2-step process in this case to try to figure out the animal. So in that case, that would classify this animal here as a cat. I'm going to undo those markings for a second. And there we go. Go back to here. So that's the idea of a decision tree. A different way of determining the correct classification is known as the k nearest neighbors method. And what you do with that is you basically look at the classification of the k, you pick whatever your favorite number is, say 3, your 3 nearest neighbors. So if you had an animal that was here, let's say, we'd look at which are the 3 closest animals to it. And it looks like, in this case, that's this one, and that one. I think those are the 3 closest. So in this case, 2 out of the 3 are dogs. So we say that's a dog. So it sounds really simple, but actually that's a reasonably good algorithm, because let's say we go over here, we have one over here. The 3 closest animals are this one, and this one. 2 cats and a dog, that's a cat. If it's a tie, like, it's nice if you choose an odd number, because then there are no ties. So you could have the 5 nearest neighbors or the 7 nearest neighbors. You could do an even number and just have to decide randomly for ties. But what that will do is basically figure out a line where it's going to probably look something like this. Like, it won't be a nice smooth line as the decision tree, where anything within that boundary will be classified as a cat and anything outside of that boundary will be classified as a dog. And it's deceptively simple. You're just looking at the k closest values to your point, and whatever the majority are, you say you're one of those. So that's a cool way of classifying as well. And then one other method that I want to chat about is the k-means clustering method. And so that would be like, if we didn't know ahead of time whether these were cats or dogs, if we just had all of these points and we wanted to group them into 2 groups or 3 groups or however many groups we wanted, there's a cool way of doing that, where you basically sort of randomly assign centers of groups and then move the groups, the centers of the groups around until everything is as close as possible to one of the centers. And you would probably end up with, a center over here and a center over here. And then you would say, if you're closer to this one, you're a dog. If you're closer to this one, you're a cat. So I didn't talk too much about that last one, just because there's running out of time and there's a lot of stuff behind it. Alrighty, and then just mentioning a little bit about how coding comes into this. So statisticians will use code all the time to fit models, including all of the ones we just talked about. So the Poisson regression model, any of those clustering algorithms that I mentioned, and the naive Bayes classifier or any classifiers. Coding is really great as well. Things like R and Python are great at graphing and visualizing, particularly multi-dimensional data. So it's easy to think about, like, a graph of like one thing versus another thing. But if you have 10 different things, how can you possibly visualize that? There's some cool ways to reduce the dimensionality of your data so that you can picture what impact is each thing having. And also a really cool thing you can do with coding is to simulate really complicated things that would be annoying to calculate the theoretical probability of, but really easy to simulate. And you can get a really good estimate of the true theoretical probability of something by using simulation. So I have run out my time. I have a little slide here if you want to ask me any questions. I also have my Twitter and YouTube channels there if you want to. I promise I'm not a fake profile. I have actual content. I have a profile picture and everything, but very happy if you want to engage with me outside of this talk. And otherwise, I'm happy to take any questions about anything at all.
Awesome. Thank you so much. Okay, we will move on to our Q&A session. So if you have any questions at all, pop them in the chat. We've also got some questions received ahead of time, which we'll go ahead with to start with, if nobody has any questions right away. Okay, no questions right away. We'll get started on a couple of the ones that were sent ahead of time. Okay, the very first one, how is it best to reach out to professors for internships?
Ooh, that's such a good question. So I guess for like a research term kind of thing, like, is that what you mean? I assume that's kind of what they mean.
I think so,
Um,
yeah.
Okay, yeah, yeah. So a lot of times departments might have kind of a centralized way of doing things like that.
Mhm.
So I know for my department, there's like a program. So I would start by going to the website of the department where they work and just search for or like poke around and see if you see research opportunities. So research opportunities for undergrad or something like that. And so depending on the place, they might have a formal program for it. If you're already sort of an undergrad student, often they'll have URAs, which is an undergraduate research assistant. There's like a formal application process for that. But maybe smaller departments won't have that, but they might have someone who just is like, oh yeah, sure, send me your resume and I'll see if there's someone interested in working with you on a project. So that's a great way to do that. If you don't see anything like that, then you could always just reach out and email. Don't be insulted if they don't reply because people might get a lot of these kinds of requests and not be able to reply to all of them. Or if they reply and say, sorry, don't have any projects right now. But if you are kind of like cold calling or like cold emailing somebody, you'd want to say kind of what your interests are. And you'd want to pick people relatively, most people will have a page that says what their research interests are as well. So you want to pick someone that aligns with your interests. So you don't want to email like a pure math person and be like, I want to work on computer science. You want to like narrow it down and email the people that you think are most interested. If you're really interested in like human computer interaction or something like that, or like one aspect of computer science, then find people who are doing that and reach out to them. But I would start by trying to see if there is a program for it that's centralized, because that would be the best way. If there is one, they'll just send you to that. So you might as well go straight to that. Great question.
That was really good. Thank you so much. We got one from Shrita. What classes do you recommend taking in high school if you want to pursue this field?
It's been a long time since I was in high school, so I don't know exactly what classes are offered. Certainly, all three maths would be a good thing. You don't have to do all three maths, but it would be really good to get exposure to all of those things. It's like calculus and vectors, functions, and data, I think, are the three courses still, roughly.
Yeah.
So yeah, those would be all really great to take. If you do have a computer science type course as well, they didn't have those when I was in high school. But if there is something like that, that would be really great. And honestly, doing stuff like this, like doing extracurricular activities, giving you that exposure is really nice. And just sort of trying stuff out, playing around with things, learning some languages. Things like R, which I mentioned, is really, really easy to learn. So I would definitely recommend checking that out. It's great for stats, and it's like really, really well documented, and the syntax is relatively easy to learn. It doesn't have like super complicated brackets everywhere and stuff like that. So it's pretty nice to learn.
Absolutely.
Oh,
I can think about that. So for everybody here, data management is very important if you want to do what Diana is doing. The Bayers that you saw and the also the decision trees that you saw, probability, that's all actually taught in data management. And I've tutored that to different students doing exactly that same type of problem sets before as Diana used. So definitely do that. Functions would be good. I think vector has been put into a calculus course now, so it's calculus and vectors now. That could also be good for that field if you want to, but not necessary. So functions or advanced functions, I guess they call it, advanced functions and data management is probably most important.
Thank you for your insight.
No problem. I know things have changed since we were in high school, right? Like it's so different now. So yeah. All right.
Cool.
Also,
Thank you,
just for
Mr.
my
C.
USA people in the chat, data and statistics are the same. Like,
Oh, yes.
yeah. So because I know data isn't provided in USA schools, so it's called statistics. So for my USA people,
it'll be the same. It'll be roughly the same. Yeah.
Next up, we have, what are some tips you have for incoming first-year students?
Ooh, I have lots. So my first tip is going to sound kind of weird, and I might actually like show you a picture. So give me like 10 seconds to grab this picture, because My iPad is upside down here. It's hard to type upside down. Where's the B? There it is. B-L-O-O. Sorry. There we go. Oh, that's not a good picture. Sorry. I wanted to Google it, not go to the, there we go. That's better. Because I want my favorite picture in the whole wide world, which is this one right here. Okay. Zoom in. There we go. Beautiful. Okay. This picture is everything you need to know about how to learn at the university level. So there's kind of different depths that you can know something at. And like the very basic level is remembering stuff. Like, so flashcards, like being able to like regurgitate stuff that you've already been told. Beyond that is understanding. And above that even still is applying. And that's mostly where most high school tests are aimed at, this sort of idea of, yes, remembering stuff, understanding how it works, and applying it to situations that you've maybe a little bit new, but mostly that you've seen before. At university, it's more on these higher order thinking skills. So analyzing, so exploring relationships between things, categorizing, comparing and contrasting, organizing informations in a way that you've never been asked to do before. Evaluating, so critically looking at a problem and saying, do the assumptions for this Poisson random variable actually hold in this situation? Do we have this, random event occurring? Is this method appropriate to use in this situation? Or even creating skills. So creating something new, taking a problem that nobody has ever seen before, or you certainly have never seen before, and building something new or constructing a model to model it. So it's a big leap to go from those kind of base level skills to those higher order thinking skills. And you have to study and prepare differently when you're going to be tested on those higher order skills than when you're going to be tested on those lower order skills. So that's what I would say. I would say, think about how you learn differently and practice those higher order thinking skills. Like nobody would expect to be able to like get really good at playing the piano by watching somebody play the piano. You have to actually play the piano yourself. So you have to, if you want to get good at doing math or statistics or coding, you have to do it. And so that's my big advice. That's kind of two pieces of advice rolled into one. But that's, I think that's the biggest difference that people struggle with when they go from high school to university, is this different level of learning that they're expected to perform at when they're not necessarily used to being tested on in those ways before.
And let me ask you too, Diana, because it's been a while since I've been in university, and the university exam may have changed. But what I remember is that, in university exams, sometimes you have a lot of multiple choice questions. In high school, our multiple choice questions are usually like the lower two tiers, the remembering and the understanding. We're testing for like their basic knowledge with a multiple choice. And then we have short answer questions, or essay questions for the top two tiers. So from applying to creating, evaluating, and analyzing. And even within our our tests and exams, we usually don't even have creating. That's usually an assignment. We give students more time to practice. But in university, you could have multiple choice questions where they could be applying questions or analyzing questions. You could have short answer questions or essay questions where you're creating and evaluating. So I think the setup for the assessments at the university is very different. And I think it takes a while for students to get used to it, even myself in first year. I don't know about you, but I know in first year was a big struggle trying to navigate through that. Mm-hmm. Is that still true?
I think so, yeah. I think well-designed multiple choice questions can still test at high levels. Like just because something is a multiple choice question doesn't mean it's necessarily low level, if they're well-designed. And so there will be a wider variety. I think there will still be some questions that just require you to remember stuff, because you can't do anything unless you can remember stuff. But there's a wider range, I would say, of levels that you're going to be tested at in the university setting.
Right. Yeah. Cool.
I actually have a personal add-on question to that.
Sure,
so I understand that there's different ways, definitely, that you get analyzed, that you get marked on and assessed in terms of university. how would you best prepare for these higher level thinking? So do you recommend like flashcards? I know some people use Quizlet or like Anki flashcards, stuff like that.
That's a super good question as well. And I would say it depends on what part you are good at. Like I think with a question, if you're like looking at a question to do, there's kind of two steps. There's figuring out what the question is actually asking you to do.
Yes.
And then there's figuring out how to do it once you know what to do. And the how is like remembering formulas, being quick with a calculator, like remembering the processes of an algorithm that you've been taught to follow. That's kind of the lower level stuff. The how is the mechanics of like how you actually go about taking this derivative or solving this integral or setting up whatever. The what, the like turning the question into, a word problem, turning it into mathematical symbols, or figuring out like, how am I going to model this situation with the vast number of mathematical tools that I have, how am I going to choose which tool to use? That what part, like figuring out what to do, is the harder part. And that kind of more ends up with the higher level thinking skills of like, out of all the methods I could use, which one is the right one to use in this problem? And so it depends which one you're sort of struggling with. If you're struggling, if you know what to do, but you mess up on the how, then definitely things like flashcards and doing lots of practice problems all the way through is a good way to go about it. If it's the other way around, once you know what to do, you're like, boom, I got this, but you have trouble figuring out what to do in the first place, then what I would suggest is start as many problems as possible. So like look at a problem and figure out the first step that you would do. And then once you get to a place where you know you could do the rest, don't bother finishing it. You want to spend the most amount of your time as possible working on the areas where you're weakest. And that always sucks. It feels good to do well, right? It feels good to like do practice problems and like, yes, I got it right. Yes, I got it right. Yes, I got it right. But if you're getting everything right, you're probably not learning. The learning happens when the struggle happens. And that's really hard. You have to kind of lean into that discomfort and be like, ooh, I don't know how to approach this problem, but resist the urge to like look up a solution, because that kind of robs you of the chance to try and practice the skill of the what part rather than the how part. Does that kind of make sense?
Another thing that I find helpful in university in learning, where your deficiencies are, and I don't know how many of you guys are doing this now, but I find that studying in groups in university really helps. You find a good group of friends and you challenge each other. You bring new questions, and you ask each other questions.
Yes.
You kind of learn how each other solve the same problem, approaching it in different ways. And that will also enrich your own learning and enrich your own problem-solving skills.
100% agree. Yeah, because nothing helps you learn better than explaining something to somebody else. Like you have to learn it very deeply to be able to explain it to somebody else. I always joke that I never understand material quite so well as after I teach it for the first time. Like I finally understood, this financial math concept after I taught it the first time, because you have to force yourself to learn so deeply if you're going to explain it to somebody else. And making up questions, even just like simple true false questions, making up questions and quizzing your friends is a really, really great way to practice.
Yeah, because when you make questions, sometimes you realize that, hey, I cannot phrase the question this way because it wouldn't make sense. And so when you read a question that is phrased in a certain way, you already know what they're asking for. And you also think of all the pitfalls and all the criteria that comes into a question. So then when you do the actual question, when you see a question, you already know what all the criteria are that you need to find. So definitely, yeah, that's a really, really good skill to have too.
Awesome.
For sure.
Thank you. That was a great answer to my question. Thank you. I appreciate that. Next up, we have a question from Francesca. She said, how did you decide you want to work with statistics? And then the second part, did you always want to pursue your specific career/field?
Yeah, that's a super good question. So when I was in high school, I was one of those annoying people who was just like pretty good at everything. Like sorry, I was a nerd. Nothing wrong with that. No, don't. Yeah, being smart is okay. Being smart is great. It just sounds weird to like brag about it, but I could have done anything. Like I thought about maybe doing engineering. I thought about being an optometrist. That sounded really cool. I thought about being a computational linguist because I loved languages. And I was just kind of like casting a wide net. Like I could do pretty much anything, but I really did love math. Like math was my first love. And like my dad is an engineer, so he was kind of a little bit sad that I didn't become an engineer, but he was like, well, okay, math is pretty good. So I applied to Waterloo, definitely thinking that would be likely where I would end up. And there's the cool thing about Waterloo is that there's not just a math major, right? There's lots of different majors within math. And the one that sort of drew my attention was actuarial science, which is like the math of insurance, roughly speaking. It's sort of combining like probability and finance together and like helping people manage their financial risks. And that sounded pretty neat. And so I applied to that program and got in and got 3/4 of the way through before I decided, yeah, you know what, that's not really what I want to do anymore. I had taken a bunch of co-op terms jobs working at insurance companies and like not really clicked with any of them. And then I took a co-op job. Waterloo has like an internship kind of program. I took a co-op job working as a computer science tutor, which is like a weird pivot, but it was the best job I'd ever had in my whole life. I just absolutely threw my heart and soul into it. It was the most fulfilling and most rewarding job I had ever had. And I was like, oh, okay, I guess the universe is telling me that I am meant to be a teacher. Like that's not what I would have expected. If you told my high school self that I ended up being a teacher, I would have laughed because like it wasn't on my radar as a thing that I would enjoy or be good at, but I loved it. And then from then on, I went to grad school. And then my favorite part of grad school was being a teaching assistant, being a TA. I didn't really I was okay at the research, I was okay at the coursework, but my favorite thing was helping students learn. And so that was basically like the final seal was you are meant to be a professor. And so then I started teaching. And so yes, that is the lesson. It is 100% okay to change what you want to do. Just because you signed up for a particular major doesn't mean you have to finish that one. There's no such thing as finishing on time. A lot of students are really obsessed with I have to graduate on time. It's like, no, you have to graduate when you are ready, when you are done what you need to do. If you need to slow down and take courses slower or like try something else out or switch majors or do a double major, I actually did like a minor in music because I was interested in that. There's room for you to experiment and take your time to find out something that you really love. Because if I had tried to just push through and like kept my head down and like become an actuary, I probably would be a pretty good actuary, but I don't know if I would be as happy and fulfilled as I am. So yes, so that's a very long-winded, answer to a question that was not about that, but hopefully that was somewhat helpful. I didn't always want to be doing this, but I'm really glad that I am doing what I'm doing.
Thank you. Yeah, Francesca says thank you. That's really inspiring.
Oh, great.
That was definitely a good explanation.
Thanks.
Next up, we got one from our twins, Leah and Serena. They said, I see you have an iPad. Do you recommend one for university?
Ooh, good question. I'm not sure. The reason I have one is because I wanted one so that I could like annotate my slides as I was teaching online. Yeah. Before the pandemic, I never had one. So this was a pandemic purchase, and I found it helpful again when I'm doing stuff. But in the classroom, normally I work. I don't use slides. I work just on the board and sort of interactively. I think it depends too much on your own personal style. Like there definitely is something about the tactile nature of writing with a pen on a piece of paper or a pencil on a piece of paper that makes like connections in your brain. But if your hand cramps up when you write too much, or you have really messy handwriting that you can't read or anything like that, then having something like this is helpful. What I would suggest is when you are like taking notes in class, or if you're sort of doing something like that, make sure that you're not just writing down what is written on the board, because a lot of stuff that's like said by the instructor is maybe even more important than what's written down. So you want to be sort of capturing not the like exactly what's written down, but the essence or the key points or the key ideas, the key takeaways, and the explanations of like why something is the way it is. So as you're taking notes, if you find that you can do it faster that way, getting down everything that's said word for word is not as effective as doing that work to sort of synthesize and decide what are the important things I want to write down. There's probably some good advice out there about like good note-taking techniques. There's something called the Cornell method, which I've heard is really neat. You sort of like divide up your page, and then as you go, when you go back over your notes, you kind of like annotate things like what are the important things to remember or the key takeaways from each thing. something like an iPad and something like OneNote or like a program like that where you can keep all your notes organized is nice, but so is a 3-ring binder. Like it's totally cool. I don't think that the technology that you use is what matters. What matters is how you decide what to write down. And that should be, again, like writing down what's important, not just only what's on the board or like word for word trying to capture everything, just capture the most important ideas. So sorry, I don't have a more specific answer, but it kind of depends on your style. And I feel like something about writing something down with a pencil just feels like it's more like your brain is connected to your hand somehow. But an iPad can have that feeling as well, if you want to keep your notes organized in that way.
Yeah, no, I totally relate to that. Whenever I have to do math, it has to be on paper or the math doesn't go in my brain.
We have another question from Jillian, but she's not here today. She sent it earlier, but the question is, what are some challenges you faced as a woman in STEM? How have you overcome them?
That's a good question. I definitely have seen some changes even over the last like 12 years or so, like 10 years that I've been, 14 years that I've been working at Waterloo, but in particular, like in the last 5 to 10 years, there's more awareness of kind of the idea of like implicit bias and just the way that different people have different access to things. So it's the kind of thing that you can have conversations about now that you just couldn't have conversations about 10 years ago. So that's a good thing. I think it's moving in a good direction. We're still pretty underrepresented in math. Like the faculty of math is like about 35% women, which is not great. I'd love it to be 50. And the other thing too is that, so higher education as a whole in terms of undergrad is more than half women, but the higher up you go to the master's and PhD level and then to the professor, like the professoriate level, that percentage gets lower and lower and lower. And so like in the department, in terms of like the faculty in my department, it's probably 20% women. It's much less. And that's so the call it like the pipeline, the leaky pipeline of like, even though more women are starting undergrad, they're not necessarily moving on to the higher levels of education. And that could be, again, a large number of different things causing that, biases, having a mentor who's like nice but isn't going to stick their neck out for you. You don't want a mentor, you want a champion. You want someone who's going to say like, hey, you should hire this person, or like, hey, you should pick this person as your research assistant, not just someone who's going to be like, oh, good job, you're doing great. You want someone who will like put themselves out there for you, and be your champion. And so yeah, I found occasionally, I haven't had any like horrendously terrible experiences, but I've had like, you might call like microaggressions of people being like, oh, wow, I can't believe you're a professor. You look so young. And it's like, that's not the compliment you think it is. Like, that's kind of like belittling my experience. And sort of, I get that a lot. I'm just like, oh, wow, are you new here? It's like, no, I've been here for 14 years. Like, I'm not new. I'm just energetic. So sometimes there's still like a little sense of like a real professor is like serious and like, you know, very blah, blah, blah. But like, no, like you can still be a professor and be young and be energetic. And there's more and more diversity of thought and of the way of being that's happening, which is good, but we're definitely not at equality yet, but we'll keep fighting.
Yeah, thank you. That's actually a really good observation. I've actually seen that quite a bit when I've like visited universities. I was just like asking like how many girls, for example, in engineering are there who are taking masters, and then how many go on to take PhDs, and they're like, oh yeah, the number goes down, like because they're pretty equal at the undergraduate level. So I was kind of surprised that also like continues in the math field. I was like, oh.
Yeah, it still seems to be a problem in lots of areas, which is too bad. Again, could be death by 1,000 paper cuts. Like nothing terribly bad happens on any one given day, but like that the kind of things build up and like societal pressure. It's still sort of like, oh, aren't you gonna like? Why would you do a PhD? Why don't you settle down and have a family? It's like,
oh yes,
you do both. Yeah. Or you don't have to have kids. That's okay too. Like I have kids and they're great, but you don't have to if you don't want to. Anyway, yeah.
Absolutely. We've got another one, which is, do you have any interview or work tips for young teens?
Ooh. So I guess it kind of depends on like where you're applying, like what kind of thing. But in general, with like interviews, you want to think about being yourself. Like you don't want to pretend to be something that you're not, because then they'll hire the person that you're pretending to be, and then you'll be miserable when you are not that person that you pretended to be. So like in a certain sense, like be yourself, but be like a polite, polished version of yourself. But you want to be someone that the person who's interviewing you can see working with you and trusting you to do what you say you're going to do. And so if you have examples of, you were given some authority over a project, or left to handle something that was maybe beyond your original description or what you planned to do, and how you handled it, having examples like that is a really great way to prepare for an interview. And there's a cool method to like respond to that type of question, which is the STAR method. So situation, what was the situation you found yourself in? Task, what were you supposed to do? Action, what action did you specifically take? And then result, so what happened in the end. So maybe like you were working at a store and there was a fire alarm, and you were the only person there and you weren't sure what to do. So you like closed the till and took this out and like did all this stuff, and then like locked the door, and then did everything that you were supposed to do without knowing that was what was supposed to happen. And then it ended up being a really good thing because it was a fake alarm and someone had like robbed a bunch of other stores. I don't know, that was a completely made up example, but the idea of like what your specific actions did and then what was the result, and having examples like that is a really good thing to do, and you can pull those examples from anything. It can be from your academics, it could be like if you volunteer somewhere, or it could be in your personal life, extracurricular type thing, whatever it is, or previous jobs that you've had. It doesn't have to be from like a working situation to be something that's relevant. And there's a lot of skills that are going to be transferable to any job, especially things like communication skills, leadership skills, teamwork skills. Those kinds of things are things that employers are looking for, right? They want someone that they can work well with and that will fit well into their team, and that they can trust. And so demonstrate your ability to be that person without making stuff up about yourself, because again, you don't want to present a version of yourself that isn't true, because then you'll be miserable when you are not that person.
Those are really good tips. Kelly, do you want to pull up the next one?
Where's the next one?
Okay, wait, no, never mind. Okay, so what are some common mistakes that you see your students make, or like weak areas that people should focus on before entering like statistics, like the program, or even just like when they actually go out into the world and like try to get a job?
That is a really good question. I think probably the thing that people can work the most on, and like not that people are all bad at it, of course, like everyone's good and bad at various things, is the ability to communicate the results and sort of apply or like interpret the math back into the real world, because that's what the world needs. The world doesn't need more people that can do the calculations. Computers are better at us than most of those things. The world needs people who can critically evaluate a situation and decide what model would be appropriate and whether the limitations of the model are worth working with, and then take the results of that model that maybe a computer did the calculations for, and then bring that back into what does that actually tell us? Should we change the regulations for car emissions? Should we build another road here or not? Should we like increase our surveillance of like financial fraud transactions or fraudulent transactions? Should we ban all the bots on Twitter? Like, how does the math, I think yes, but that's pretty obvious. But thinking about how the mathematical result can then be interpreted back into real world, because it doesn't matter how good your model is or how perfectly it fits. If you can't convince the decision makers about what it's saying and why that's important and why they should listen to it, then all of that work was for nothing. So I think that's the skill that's the most needed. And a lot of times I see people sometimes going into math and just being like, when I ask them to like write a memo summarizing the work that they've done for a statistical problem, they're like, what, you mean I have to write a sentence? Like, what? I didn't come to math to write sentences. I'm like, oh yes, you did. You got to write a whole bunch of sentences for me. One person even asked like, so this course is basically an English course now? And I was like, yes, I'm going to make you write reports. I'm going to make you write so much. You'll wish you'd never been born. No, I didn't say that. But the math is only as good as you are able to communicate the ideas from it to an external audience. And so that's a skill that I think everybody needs to get better at, including myself.
That's a really cool idea, because a lot of times you just think math it's just all calculations. You never think about the communication side of it. So that's a really key idea. Do you think that that's something you should try to develop earlier? Like how or much earlier?
All the time. Like for all the time. Yeah, like anytime you're thinking about, even in the courses that you're in now, it's nice if you can explain the math that you're doing to a younger sibling or a parent who doesn't have a math background or something like that, or like think about how you would make this idea clear to a decision maker who doesn't have the technical background. Like think about how you can use an analogy to make it like this thing is kind of like that thing, that can make it easier to understand. Yeah, super important.
Awesome, thank you. Also, how did your earlier career choices lead you to where you are now?
Kind of meanderingly, I guess. I kind of talked about this a little bit before, but yeah, I just noticed Ken's point there. The teachers always ask you to answer a word problem in words. It's not just because they hate you, it's because that's an important skill to have. So forgive your teachers when they ask you for that, because there is a reason that they're trying to get you to think about. You want to state your final conclusions in the context of the problem. So if it is annoying, I understand, but the reason is a good one. That's what you need to be able to do in the end. Sorry, back to the question. Yeah, I just kind of, this is going to sound a little bit cliche, but I just kind of did what I liked. I kind of followed my heart into teaching. And then I found that I was reasonably good at it. And then as I got more advanced in my career, I started mentoring other younger teachers. So helping them out with developing their teaching, sharing my materials, pointing them to like teaching conferences to go to. I started speaking at conferences myself. I've spoken in like 4 different countries now, which was pretty cool. One of them was Indonesia. So that was like, the others like Canada, the US, and the UK, which is like not that weird, but I got to go to Indonesia and like do a teaching seminar on how to teach to a bunch of instructors over there, which was really amazing. And so like, as I started learning more and realizing that like, oh, I actually do know stuff, I can share it more widely with other people. And then that sort of culminated in this job that I literally just got like 6 days ago, July 1st, is the math faculty teaching fellow. So I'm sort of, my job is still to teach my own classes, but also to help all the instructors in the whole math faculty at Waterloo improve their own teaching skills and try new assessment techniques and do teaching research and go to teaching conferences and just sort of build up their professional repertoire of teaching. So I just kind of, like followed what I was good at, and it led me in a great direction. I was very lucky.
Congratulations on that.
Thank you.
I have one last question. I have one personal question.
Yeah, sure.
But before I ask, does anybody else have a question in the chat?
Oh yeah,
because we're almost at that. We're past time. Just make sure.
Yes.
Okay, I'm going to assume not. But if there is a question, are you open to? Sorry, I'm putting you on the spot. But are you open if we can just email it to you later?
For sure. Oh yeah,
okay.
Absolutely. Yeah.
Okay, thank you. My personal question is, what's your favorite class you've ever taken in university?
That I
very broad.
Oh my gosh. There's
I plan on going to Waterloo too.
I had so many great classes, and like for me, the classes. For me, it was almost always about the professor. Like a really good professor can make any class amazing. Absolutely. And I've had lots of really, really great professors. So like, oh, I can't pick one. It's too hard. They're so good. I think one of my favorites was actually music history, like medieval and Renaissance music history. It was only offered once every 2 years. And I waited, like I wanted to take it, but then it wasn't offered and then it was full and then whatever. So in my very last term, I finally got to take this course that I've been waiting my entire degree to take. And I was just like, I smoked it. I got like a 98 or something ridiculous in it because I was just like in every class, I was like, this is so exciting. I'm so happy to be here learning about this cool stuff because I love music and it was great. But yeah, in terms of my math classes, there were so many really good ones that it would be so tough to pick one.
I'll just take one of them if I get there. If I get it.
You should try to take the music Renaissance class.
Music
it was great. Honestly, it was super good. But yeah, I loved. I was also in my very last term. There was a really cool course where I remember getting the assignment and being excited to start it. Like I read the assignment, I was like, oh my God, I'm so excited I get to do all this cool stuff. Because it was like, by the time you get to 4th year, you can do real stuff that's like actually like relative, things in first year and second year are maybe like a little bit simplified because they have to be. You don't have like super fancy actuarial techniques. But by the time we were in fourth year, we could do like mortality modeling with like real complex data. And so I remember like literally being excited to start an assignment. And then I was like, oh, wow, this is going to be fun. And that was one of my favorite professors as well, who still teaches at Waterloo too. And so every now and then I get to tell her how she was my favorite instructor, and she goes, ah. But actually now 3 of my former students are also professors in my department.
No way.
And like 2 of them are like right down the hall from me, although now nobody's down the hall from anyone, but normally there are people in halls with me. And it's really cool to just see like, if they teach a class that I taught them, I kind of see myself reflected in the way that they teach. And that's just like, my heart. Just like my generation shall live on. It was very cool.
Oh, we do have another one.
Mhm.
Oh, how do you usually handle the stress of learning new topics and juggling homework and assignments? What's a relaxation technique you use?
Yeah, that's a super good question, because there's a lot. Like if you're taking a full course load at Waterloo anyway, it's 5 classes, and that's just there's a lot of information coming in every day, and your brain can only handle so much at a time. So what I would suggest is never study one thing for more than an hour at a time. Like your brain is going to reach like saturation levels of knowledge, and then anything else that you study, you'll just forget. Like I'm not being very scientific about it, but like there is a very clear drop off in how much you retain. If you study for like 5 hours, you learn basically no more than 4, and 4 is barely any more than 3. The sweet spot might be different for each person, but I would suggest like try to keep your study sessions short. Don't do like a marathon. Do like 1 hour on calculus, and then do what you can, and then go do something active, like take a break, have some water, go for a jog, do like some, whatever, impact training, whatever, just do something other than that. Maybe like if you're taking electives, switch to a different class. If you're taking like maybe an economics class or a language course or something, work on that for an hour, and just don't try to like do too much of the same thing all at once, because your brain is just going to be like, nope, too much, saturated. This is all the math I can handle for today. And then when you sleep, your brain will kind of like sort and reorganize that information. And then the next time you want, like if you review it again, your access to it will be faster. So kind of use your neural pathways, like hack your neural pathways to remember the things you want to remember by spending short amounts of time on the things that you really want to remember, rather than trying to like cram it all out. It's, again, there's study after study shows that like studying for 4 hours total, 1 hour each day on 4 consecutive days, you retain more doing that than doing 8 hours at once on one day. So like half as much time just spread out over 4 days is going to be more effective than like giant cramming session right before the midterm. So everyone always says that, but like they've done experiment after experiment after experiment, and it's always true that like spreading it out is better in terms of your retention, how much you're going to remember, like and how easy it'll be to access it, because you're sort of refreshing those neural pathways every day instead of trying to like put it all, cram it into your short-term memory. That's not a great way to do it. It's a great way to stress yourself out. So spread it out, make a plan, and that's a better way to avoid too much stress at once.
Speaking of cramming, this will be the last question. This is just a personal question from somebody who is sort of a chronic procrastinator, but still tends to do well. How do you break that cycle? Especially like I'm going to first year, I know there's going to be a lot of work and I cannot be cramming everything before. So how do you spread things out?
That is an excellent question. And if anyone knows the answer, I would love to hear it, because I also need that advice. I too am one of those people who leaves things to the last minute, and then they always seem to work out, which is dangerous. It's a dangerous position to be in, because you start to rely on that. Yeah. And so I'm gonna give you some advice that I actually did follow and actually successfully followed when I was getting my professional actuarial designation. Mm-hmm. It was kind of a big, long project of like, it was more than a year to get this all done, including like 3 professional exams and all of these modules that I had to take. Mm-hmm. And I was like, I know that I am a procrastinator. There's no way that I could possibly do this if I don't plan it out. So I got a spreadsheet, and I put everything I wanted to do in column A all the way down to like row 50 or whatever. Mm-hmm. And then every day of the week along the top in column like B, C, D, whatever, every day. Mm-hmm. And then I planned out, okay, like for big milestones, so like this exam, that exam, the other exam, and then within that sort of like sub milestones of like, okay, chapter 1 of the material, chapter 2 of the material, chapter 3 of the material. And I planned, okay, for this week, I'm going to spend 1 hour on this chapter, and then the next day, 1 hour on this chapter. So I actually like sketched it out of like how much I was going to spend on each thing, and so that I would hit my milestones. And I realized when I was planning this out that there was no way I was going to be able to do 2 things so close together as I had originally scheduled them. There was just, with all my job and everything, I realized there's no way I could do an exam in June and another exam in July. And so I realized that early enough to be like, okay, I'll do the exam in June and I'll do the other exam in November or something, so that I like knew that I would have enough time to do it properly. And then I kept track of how many hours I spent on each thing. I just like in my giant spreadsheet every day. I hardly ever did more than an hour a day. Again, my brain doesn't work super great. I had a concussion a few years ago and my brain still can't focus for too long on one thing. So I would just be like, okay, today I'm working on chapter 3. So I would do an hour of work and then be like, well, that's good. Put a 1 in my spreadsheet and close my books and then go back. And so then I could look back and be like, ooh, look at all these hours that I've got. And I'm following, like I could see if I was getting behind or getting staying on track, which is really, really cool. And so normally I have a lot of trouble with that. And the only reason it worked and the only reason I was able to do the whole thing was because I planned it out. It was too big of a project to like wing it like I normally would. And so I'm glad that that I did that. And I wish that I could be that good at other things planning. Normally I do still leave things to the last minute, which is bad. But try that out, see if it works. There's lots of like productivity apps and stuff, but I just found like a straight up spreadsheet where I put in a number for how many hours I worked each day and on which thing. Because then at the end too, I could like see the total, and that was kind of neat to like see my progress and stuff. That was cool.
Awesome. Thank you so much. That is all we have time for today. Kelly, would you want to close us off?
On behalf of Comodo Coding Society, we would like to say thank you to Miss Diana, Scott, Skill, oh geez, it's really difficult for me to pronunciate some things, but Diana Skrzydlo, Professor Diana Skrzydlo, we really appreciate your talk, and you definitely inspired me and definitely everybody else in this room. And for me personally, I actually didn't see the connection between data and real life because I took retail data this year, and I didn't really see the application and anything I was trying to do in the future. So now I really got it down.
Awesome.
Thank you.
Well, thanks again, everyone, for having me. It was really lovely to be here. And yeah, please do reach out if you have any questions. I think my email is somewhere. I can send the slides to you actually if you want to share them with the group. That has my contact info in it. So
thank you so much.
Awesome.
Everybody, thank you so much for coming. Really appreciate you coming out and listening to this on a nice summer evening. Also hope you guys are able to come next week. We're going to be going over some fun stuff. We're going to go over your projects and handing out prizes. Ooh, yes, and certificates. But thank you so much. Have a great evening, everybody, and hope you enjoy the rest of your summer week.
Thank you.
Everybody, round of applause in the